All right, so we are moving into a new section, section 6.3, which is called trigonometric integrals. And basically it comes down to how do I handle integrals that have trig functions in it? Don't like it already. Already, I am predisposed to dislike this section. What if I told you this is going to be awesome? Trigonometric integrals. All right, here is a problem from your 6.1 homework. All right, that says, real quick example, what if I want to integrate sine squared x times cosine x dx? I see a product there, but it's not going to be an integration by parts problem. This is going to be a substitution problem. Can anybody foresee what I should set u equal to? Go for it. If I let u be sine of x, what does that make du? Cosine x dx. And I look at that and I say, oh, in terms of substitution, that lays everything out for me, right? This is du, and this is u squared, right? Again, substitution says take a complicated looking integral, rewrite it as something that looks simpler. This becomes the integral of u squared du. Antiderivative becomes 1/3 u cubed plus c. And then since this is not a definite integral, I'm not getting a number back, I'll substitute back 1/3 sine cubed x plus c. Here we are with that. All right, now what if I were to make this look, in some sense, way more complicated? Instead of sine squared x, what if I had sine to the 200x times cosine of x dx? Not that I would ever think that you really needed to know this integral or calculate it. Like the design of a bridge hinges on accurately knowing the antiderivative of sine to the 200x times cosine of x. It's not going to happen. This is just sort of in theory. What could I do? It's the same thing, right? If I let u be sine, du is just sitting out there right in front of me, right? Ah, okay. If I let u be sine of x, du is cosine x. This whole thing turns into u to the 200 du, right? Because 1/201 u to the 201 plus c, 1/201 sine to the 201th power of x plus c. So in some sense, I don't care what power you give me for sine. If I have a cosine laying around, then Bob's your uncle, right? I don't know, but it is. Now that I've used that phrase, you're just going to have to kind of watch out for when other people, use that phrase. Right? It just makes it funnier, right? There's just certain times, and I don't. Yeah, this is just one of the cartoon quirks, I suppose. But you ever heard of people like making reference, like turning the dial all the way up to 11? You heard that before? Do you know what that's from? All right, so do you know what a mockumentary is? Like watch The Office, right? The Office is a documentary of people working in an office, but it's for humorous, whatever. It's not a real documentary. It's a mockumentary. It's a humorous thing, right? So if I know correctly, the first one is this one movie called This Is Spinal Tap. It's about a fake heavy metal band called Spinal Tap. And it's a documentary, but it's all just done because it's all scripted and everything like that. It's a mockumentary. I have never seen it. It was like when I was a little kid, I think when it came out, right? So it's old, right? But at one scene, this is a super famous scene that the heavy metal rocker dude is showing the producer, the interviewer guy, his band equipment. He's like, and this amp, he's a British, is special. Whatever, I could show you the video, but whatever. He says, because this amp, the dial goes all the way to 11. You see, like most amps, they stop at 10. But with us, if we need just that little extra, we can just turn the dial up to 11. We get that little extra more. And the interviewer's like, but why don't you just like make your amp louder and then call the biggest number 10? Wouldn't that be the same? And the guy looks at me and goes, but this amp goes to 11, right? You know, so if you know that backstory, you can hear people talk about cranking it to 11 all the time. I guess maybe folks my age, whatever, but it's still, you can hear that reference. Greatest movie of all time is Spider-Man Into the Spider-Verse, right? I'm sorry you didn't realize that at first, but if you watch the director's cut stuff at the end of it when they talk about it, like that, have you seen the movie? Okay, so I'm surprised you didn't recognize that it was the best ever, right? But the end when like the whole world's collapsing, whatever they do, all that kind of stuff, it's going crazy, and Miles is taking over his powers and like has control, all that kind of stuff, right? The directors say, yeah, when everything's going nuts, we just crank all the dials to 11 and blah, 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 blah. And he keeps on talking. And it's like, yeah, he knows what that means, right? Anyway, so have no idea how we got onto that. All right, next example, ready? This next example is going to crank it to 11. Now, we'll find out. Never mind. All right, throw all the phrases together. Now, seriously here, what if I did sine squared x cosine cubed x dx? Does that feel like it got way more complicated? It's okay if you say yes. If you think no, I'm also fine. To me, though, okay, correct. This is what I want to do. I want to let u be sine x, and then du is cosine x. But I don't have cosine x, I have cosine cubed x, right? That's different. So now the trick is, this is going to work, but I got to do some algebra. What I'm going to first do is recognize that this is sine squared x times cosine squared x times cosine x dx, right? This is going to be one of those cases where you can say, I agree, I don't know where you're going, but you haven't done anything false, right? And then I could say that again, u is sine of x, du is cosine x dx. Part of my integral feels good because this becomes du. Again, this becomes u squared. But then the question is, what happens to my cosine squared x? Right? Is everyone tracking with me? That's the last piece that I have to resolve. But we have a famous theorem that relates sine squareds and cosine squareds together. What theorem is that? Starts with a P and rhymes with Pythagorean. Man, you guys, so quick. Pythagorean theorem says sine squared x plus cosine squared x is 1, right? So Pythagorean theorem, I'll write over here. Sine squared x plus cosine squared x equals 1, which means cosine squared x is the same thing as 1 minus sine squared x. So I could rewrite this as sine squared x times 1 minus sine squared x times cosine x dx. And now do you see why that's advantageous? When I make my substitution, I have a u squared. In parentheses, what do I have? I have a 1 minus u squared, and then a du. And now I need to do some algebra. Now this is just polynomial stuff. This is what u squared minus u to the fourth du. Antiderivative of u squared is, right, 1/3 u cubed minus antiderivative of u to the fourth, 1/5 u to the fifth, plus a c, and then do a final substitution. I have 1/3 sine cubed of x, minus 1/5 sine to the fifth of x plus c. Everyone track with that? You have questions about that?
Yeah.
I have questions, but I'm not sure what to ask.
Exactly.
You okay?
I guess the first thing that comes to my mind is, where does your brain jump through the loop to recognize?
Yeah.
Oh,
So
wait, I could use the Pythagorean theorem here.
what is mathematics? I think we talked about this before, but my classes blur together. My quick and dirty definition of mathematics, it is pattern recognition. Recognizing patterns and developing them further. So what pattern am I looking for here? That's what basically you're asking, right? Okay, one pattern that I recognize is that I have sines and cosines raised to powers. Okay, that's the first step. The second step that makes this tick is that I have at least one of these two powers being an odd power. Because when one of these two is odd, I can strip it off and take the remaining even stuff and turn it into like this cosine squared or sine squared thing because of the Pythagorean theorem, and then I can substitute. That's the key that we're looking for. So let's do another example, and then I'll show you in the book where this is written now. And because it's a math book, even though it's one of the best math books ever written, because it's a math book, some of this stuff just feels dense when you look at it. And like, oh, that's what I was supposed to get out of it. I didn't catch it the first time around. If you read the examples, it'll make more sense than just reading the theorems alone. All right. What was the cliffhanger problem that I gave you on Wednesday? So we're going to come back and solve this problem. Do you remember? I think it was it sine to the eighth, cosine to the fifth? Does that sound familiar?
Yeah.
Derivative of sine to the fifth plus cosine to the third. Or cosine to the eighth. Oh wait, yeah, 5 and 8.
All right, sorry. So sine to the fifth, cosine to the eighth, sine to the fifth x, cosine to the eighth x dx. Perfect. All right, so what I'm going to do is I'm going to do a bunch of algebra. This is the same thing as sine of x. Oh, this is my pattern. I had an odd power, right? And now I'm going to go slow motion here, as in I'm going to take an extra step just to be extra slow about it and make sure that you're tracking, because it's the first time of fully developing this theory. I have this one sine by itself. I want to turn sine over here, sine to the fourth, into cosine. So key to that is recognizing that sine to the fourth, this will feel kind of silly, is sine squared squared, right? Everybody all right with that? Yep.
Why would you change the odd number? Why would you always go for the odd?
Because I want to be able to have this sine dx or a cosine dx. And then even powered stuff, I can use Pythagorean theorem to convert over to the other stuff. All right, so sine squared inside my parentheses turns into, I'm gonna put this sign next to the very end now. So I'm gonna jump into parentheses. Inside the parentheses is 1 minus cosine squared x squared times cosine to the 8th x times sine of x dx. You catch that?
Wait, I thought it was.
Did you get it? Okay. All right, I think I've been telegraphing it, but let's go ahead and ask it as a question. What am I going to now use for substitution? U equals what? No. Cosine x. And in this case, du is what? Close. Negative sine x. That means negative du is, oops, there's a dx over here. Sine x dx. It's a lot of algebra, I know. Do you see where all that's going? All those different pieces, how they come together? And now I am firmly in polynomial land. And I don't know about you, but I am much more comfortable with polynomials than I am with trig functions. And so you throw any kind of integral of, here's a long polynomial, like, that's fine, whatever, and just take it step by step. And so now I have 1 minus u squared squared u to the 8th du. I'm going to throw a minus sign out front, right? And then I got to square the things in the inside. That's going to be 1 minus 2u squared plus u to the 4th. Think about how you square something, write it out step by step if you need to. And every step that I'm taking here is just an algebra step, right? Everyone all right with all those steps? So far, like 90% of this problem has been algebra. I did an algebraic rewrite up here. I did an algebraic or trig rewrite up here. This is a calculus step where I found a differential, and then a substitution, that's algebra. This is algebra. This is algebra. Now another calculus step. Let's actually find antiderivatives. Antiderivative of u to the 8th is? Antiderivative of negative 2u to the 10th? Negative 2 over 11 u to the 11th plus, there you go, 1/13 u to the 13th plus c There's that minus sign living out front. I'm going to bring it through. So -1/9. Substitute back. Cosine to the 9th x plus 2/11 cosine to the 11th of x minus 1/13 cosine to the 13th x plus c. Doesn't that look crazy? Yeah, it is. It is long.
So the thing that comes to my head is, what's the likelihood we'd have to do a definite integral for something like that?
Maybe in the homework there's something like that as far as a definite integral. Like on a test, probably not, just because it takes a while to get there. So you saying that this looks long, does remind me of something, which is, in my mind, there's a difference between long and hard. They can sometimes go together. But if I just brought in a bunch of like just raw metal and I said, build me an engine, well, that's hard. I mean, there's a lot of design, a lot of planning and all that kind of stuff. I don't know. If I handed you a shovel and said, go to the drill field and I want you to dig for me a 4 foot by 4 foot by 4 foot deep hole, it could take you a while, but every step of the way, you know what you need to do next, right? I need to dig again, and then again, and then again, right? It's a different kind of hard. One will wear you out physically more than the other, sure, but it's a different kind of thing. This here reminds me of shoveling the dirt. And it's new to you, so you have to think harder, right? But if you think about, okay, I'm going to pull off one of these odd terms of sine or cosine. I'm going to convert all the even stuff over to the other trig function, and then do a lot of algebra over and over. When I actually get to the final calc step, it's not that hard of a calc step, right? It's everything that I'm doing is gearing me towards being able to replace all my sines and cosines with polynomial stuff. That's what I'm shooting for. Does that make sense? Not to say that it's trivial, right? Not at all. But there is harder stuff that we have to do sometimes. And this one is relatively formulaic once we have some practice. All right. There is another kind of thing. Well, I can show you real quick in the book. In the book, there is this big key idea, which is super daunting. But it basically says when you have sine to the m, cosine to the n, I either want m to be odd or n to be odd, and then I can do some substitution where it comes down to peeling off one of these things. If you sort through all this kind of stuff, it will explain to you what we just did. And then if you're in a case where they're both even, it's most unfortunate. There's a different algebraic step to deal with that is just also some drudgery. The goal really is not that you become experts at integrating sines and cosines raised to various powers. Rather, the goal is the problem-solving process, making you think like a mathematician, making you think, in some sense, like an engineer, step by step by step. What do I need to do next? That's our real goal, but we're practicing it through this integration process. And then there's another set of integrals that I was planning on getting today. We didn't get to it. That was actually tied into that linear stuff that I was going to show you anyway. So we're going to punt that for Monday, but I'm glad we still did a review of that other integration technique. That was useful, I think. All right, so that'll end class for us today.